In this video, we are going to talk about precise current measurement from very low currents up to 10 amps. And we are going to go into details. We are going to talk a little bit about schematic. We are going to talk also about what is important and how to design this kind of circuits. So everyone who needs this kind of measurements or who is designing this kind of devices, then it can be very interesting to watch this video. Is this what we are going to talk about, Matt?
For sure. Yeah, looking forward to talking about Joulescopes, how we make great current measurements, great voltage measurements, and can actually help people design awesome products that are lower battery power, are longer lasting. And we have a whole bunch of things to talk about with analog signal chain, with processing, the TI parts that we use that help enable the precision that we're now delivering with our third generation product, the JS320.
And we are going to talk also to Josh. Josh is from Texas Instruments. And Josh, what you are going to help us with? I guess with, you know the Texas Instrument components, correct?
Yes, yep, I'm familiar with the Texas Instruments portfolio. I'm Josh Brown, a product marketing engineer. I'm with Texas Instruments, specifically on the precision ADC team. And Texas Instruments has a very broad portfolio for test and measurement applications.
Okay, so before we completely start, I would like to say why Matt is the right person to talk about this topic. Because all over the internet you can find all the kind of videos. You never know who is talking about specific topics. Sometimes these people, maybe they don't really know what they are talking about. So Matt, why you are the right person?
Well, I've been working on this in one way or another for almost 10 years now. So I'm the creator of Joulescope. The first version of the Joulescope, the JS110, we launched on...
you can show your page. I think there is a page with the Joulescope, correct?
Oh, yes, I can. Let's see, here we go. So it started out with the JS110, which we launched on Kickstarter in 2019. Our second generation product, the JS220, we launched in 2022. And we're coming out with the JS320, which is launching just in June here. The evolution from here is going from an instrument that was great to an instrument that is even more accurate and precise to now the JS320 that's going to even be more accurate. And we're building on this over time, improving and learning things as we go. And right now, the JS320 is really built on a whole bunch of TI parts that enable the accuracy and precision that we need in order to deliver the JS320.
What can we do with this
Matt,
device?
I like how you... Sorry, go ahead, Robert.
What can we do with this device? Can you be more specific?
Sure, yeah. With the JS320, it measures simultaneously voltage and current. That's really what it comes down to. Then it can multiply that together to compute power, and then integrate over time to compute charge and energy. And with that information, if you're designing a product, you can optimize for longer battery life or lower energy consumption. So you can plug in your normal setup, whatever you would normally be developing, put a Joulescope in the middle on the current side, and it allows you to instantly see your voltage and current consumption. You make changes in real time and you can instantly see that change and how much you've affected your battery life.
Mm-hmm. And I think what I would like to highlight, because maybe some people, if they don't know Joulescope, maybe they can be like, oh, I can use DVM or something. I think what is one of the really important things to mention, you can do measurements very quickly. So actually we can see even like instruction level of current consumption, for example, of a microcontroller, correct?
Yeah, for sure. And one thing that's different with the Joulescope compared to like a DMM is it's super fast auto ranging. So typically with the DMM, it will auto range and take, the fast ones are about 3 milliseconds. In that time, if you go from microamps all the way up to an amp, your device is going to brown out. So the way that you have to do it with a DMM is you set your device up in different modes, measure each of those modes independently, so it's a manual process. Whereas Joulescope, it's high dynamic range. It measures from nanoamps all the way up to 10 amps, seamlessly auto-ranging, super fast so that your device always keeps working, no brownout, 20 millivolts burden voltage, so it's super low burden voltage, meaning that your device barely knows that Joulescope's there. Whereas a multimeter, some of them are 0.6 volts or even more at the higher current ranges.
Again, I would like to highlight, you can even see like when, for example, your modem is connecting to network, when your Wi-Fi is sending data, you can see all these current changes. That's how precise it is, correct?
Definitely. And what you see behind me, which we'll be looking at in a little bit, is a demo where we can show just two different setups, one that is much more controlled and one is much more like a real product. It's using one of the TI eval kits for the Bluetooth low energy products.
Okay, let's go back to the schematic because I think many hardware design engineers are
I do
working.
briefly want to touch on
Okay, good.
I am happy that Matt brings up the ADCs on this part because how the ADCs help to enable each generation of the Joulescope that he's designing. And I do want to point out that a lot of the ADCs that he was showing, the ADS 7056, the 9226, and the ADS 127L14, have been multiple generations that we've been targeting towards test and measurement applications, specifically integrating features like with the L14, a lot more digital features, which I assume we'll touch on later in this video, that the L14 enables a much higher flexibility with the features inside the ADC chip itself. And even in the future, we're looking into integrating anti-aliasing filters inside the ADC chip to reduce the overall burden on external anti-aliasing filters in signal chains.
I think we already started this topic to make it look more complicated because maybe some people, they think I only need ADC and I can measure whatever I want, but it's not so simple, correct?
Of course, yes. You always need some sort of front end, either to drive the ADC or to do some sort of filtering to feed into the ADC chip itself. Now, of course, in the future, we're always looking to make it easier on the customers, whether we integrate inside the ADC chip or we improve the external amplifiers to make the overall signal clearer for the customers.
Okay, now we can go back to the schematic because I think the schematic is exactly what is before the ADC, correct?
Exactly.
Correct. Yeah. So this is the analog front end. So typically with any system that is not just directly into an ADC, which most analogs, acquisition systems have something in front. This is what is in front for Joulescope to convert the input signal into what we drive the ADC with. So it starts out with a shunt resistor over here. Joulescope is a shunt ammeter, which is just a fancy way of saying that it measures voltage over a known resistance and then multiplies that together to compute current, or it actually divides. So V equals IR. So current is equal voltage divided by resistance. And in order to compute that voltage, we need to amplify it up. So Joulescopes have a full-scale range at their input of 20 millivolts. That's the maximum burden voltage. And in order to get from that to what the ADC wants, we have to do some gain. With Joulescope, it's super important that we measure accurately. Ideally, this resistor is a fixed known value that never varies. Everything in the signal path is a constant gain with no real world problems. It's all ideal. And then you go into an ADC that's ideal. Unfortunately, real world problems come into play. So engineering is all about trade-offs. With the signal chain we have here, we've selected for precision where we need it. And as you can see, we have a number of different parts. We have an OPA 387, OPA 387, OPA 388, and an OPA 323. We've actually selected these parts very carefully. It's not an accident that they just have different numbers. They're all selected to meet the performance needs of that stage of the signal chain. So when we start out at the very beginning here, we have the needs of low-level voltage measurements. Those have to be accurate over time, temperature. Input bias current is a huge thing because we're trying to measure down to nanoamps. So this front-end op-amps input bias current is super important to us because any of that is actually real measurable current from your target device. So that has to be super low. And then as we go through each of these gain stages, the demands of the offset performance, gets less and less, but still is important to us. We've selected parts here, the OPA 387 and 388, that are zero drift op amps. And what that means is they have extra circuitry just built into them that helps them maintain their performance over time and temperature. So we don't have to worry about that. But it makes it so that, we as Joulescope, TI has to worry about it a lot. It makes us just be able to design a signal chain that works over all the time and temperature requirements that we have. The OPA 388 here doesn't have quite as good of an offset performance as a 387, but it's a little bit lower noise, higher bandwidth. So at that stage of the signal chain, it's the right selection for us.
This was actually one of my questions. I wanted to know like why you used 4 of them. So basically, if I understand right, each of them has very special features which you need for each this step, but you can't have one with everything. That's the biggest problem.
Right. It makes it so that we can select for the right features at the right place. The thing about these precision op amps is that they don't have, a 1 megahertz, or gigahertz bandwidth, gain bandwidth product. So what we have to do is we have to choose our gain stages so that they maximize both the bandwidth that we need and also noise and performance dynamic response. So with the Joulescope, we're aiming for about 200 kilohertz of analog bandwidth, which is pretty high from a precision perspective, pretty low from a high-end oscilloscope perspective. But it is enough of a challenge to get that precision, that offset performance, to get nanoamps. It's really just not done, not possible without these type of parts. And our competitors, that are out there, also struggle to get high bandwidth current measurements just because it's so difficult to make these dynamic range measurements.
What about the last one? Last one looks different.
The last one is different. Yeah, so the first 3 here are all gain stages with some RC filtering. So 5, 5, and 4.5. The last one is actually an intentional filter that we're using as our anti-aliasing filter going into the ADC. The ADC, we're running at 16 megahertz as a delta sigma, and this last stage provides a maximally flat filter, the second order Bessel filter, that drives that ADC input. In the previous generation, the JS220, we used a 6-order Bessel filter. So one of the things, like Josh was saying, is the newer filter, or the new ADCs have filtering built into them that make our life a little bit easier on the analog side.
Okay, Josh, would you like to add something about these components? Like, you are very proud of them, so why?
Yep. So I think Matt covered it greatly there. It's all about trade-offs. So when we design our op amp specifically, we have to focus on the trade-offs between either offering low power, offering high precision, low noise. So we try and target a very broad portfolio so that we offer the multiple types of op amps to all types of customers. So depending on what your application requires, we have an op amp that can meet that need. So we try and design to meet all of the needs while still designing good op amps.
So if someone is designing this kind of circuit and they don't know which one to choose, what would be the steps, or how they can get advice or find what kind of op amp they really need?
Sure. So on TI.com, we have tons of collateral that help to decide which op amp you specifically need. You can go on TI.com. We have a lot of different apps, collateral, specifically application notes, application briefs that describe how to choose an op amp, how to pair an op amp with an ADC, how to design the entire signal chain. I think I'd also pose this question to Matt because one of the things I admire about Matt is he was able to design the entire signal chain with very little help from TI, using a lot of the resources we had on TI.com. So I would like to ask Matt how you were able to pick out these op amps and design the signal chain using the collateral on TI.com.
Lots of time and thought, and well, it's been also almost 10 years now of iterating. So yeah, so basically finding parts is a challenge as an engineer, right? So if you're designing hardware, just knowing what's out there, if you don't know what's out there, you don't even know what you can do with it. So you can start by having a concept, but that very, very quickly has to go from a concept to something that can be implemented. So with the way that I've approached this, I pick really the key performance criteria for where I need in that stage. So let's take a look at the first op amp here. So input bias current is incredibly important. Offset stability is incredibly important because I'm trying to measure down to nanoamps, which ends up being 0.1 microvolts on the input. So it's super small amount. So that offset stability is really important. The noise performance is important. I would like even better noise performance, but there's a trade-off you have to make. I would ideally like zero. No one wants noise. You want zero noise, but
Ideally, yes.
ideally, but that's not possible, right? So you have to trade off. So what I've done throughout all of Joulescope's life is trade off noise, so more noise for better offset performance. So that means that your temporal resolution is a little bit less than it could be if I went to a higher bandwidth part, but it means that the accuracy of measuring current, measuring power, energy, charge, all ends up being much more accurate over time than it would be if I had a lower noise part. So you have to kind of prioritize what you want so that, in this whole vast array of available op amps and parts, from like TI's portfolio, you can then narrow down and look for the parameters that matter to you. This happens to be the best performing input bias input offset device that they offer, that TI offers.
So did you
at least
try
right now.
different chips and measure them, or how did you come up with the final solution?
Yeah, so again, this has been several iterations. The JS110 used a totally different chip. That chip had some problems. It was not a TI chip, actually. The JS220, I went to TI chips, and their performance, I actually used an OPA 388 at the input stage. The OPA 387 wasn't available when I designed that. It was, several years ago. Now the 387 is out, and it fits nicely into this, gap that I would have liked to have had for the JS220. But now I have the part. So, TI is continuing to improve parts to address needs like the precision measurement that Joulescope makes. So yeah, just figuring out what's available, keeping an eye on what's coming out that's new. Is it just part of the challenge of being an engineer and developing great products?
I'm curious now because you are really stressing how important the component selection is. And very often what happens if a device is kind of simple and easy to replicate, then the clones are starting usually popping up. So this is what the clones make cheaper and bad because they don't really understand what they are doing. They use all the kind of components, or is this what do you think about like component selection and can you use just any components, any resistors, any capacitors, any op amps, and it will work always the same? Or
well, let me tell you a different story. So people use Joulescopes to measure current consumption for products. One big thing that is a very common problem when you go kind of off-brand with MLCC caps is that some of them have huge leakage currents, which is really surprising. Huge, meaning microamps, which when you're developing a battery-powered product, that could blow your entire sleep budget. So in some ways, the capacitor is going to work. It's a valid MLCC cap. It does what it's supposed to do. It just happens to have higher leakage current. Capacitors normally should have zero leakage current if they're ideal. So yeah, selecting components and selecting components from reliable suppliers, especially when you're producing, a test instrument like Joulescope, is super important because I even though I go through and test every single one of these in the factory to make sure all of them are working, if I have 5% yield fallout or 10, 20, that would totally kill the product. So we're able to select quality components that help us just push these through our factory. And also maintain a level of consistency and quality and reliability that all of our customers need.
So it's not only about op
Matt,
amps; it's about all the components.
it's all devices, yep. And I do want to build off of what Matt said, especially when you see these clones pop up, a lot of the time they'll cut corners to save on costs. So a lot of the devices need to be spec'd over temperature. And in our data sheets, we try and spec over a wide temperature range. Especially with these clones that I've personally seen, is they'll cut those corners and the device will drift spectacularly over temperature and it'll completely ruin the final product of whatever the customer's designing. So I think to Matt's point, it's very important to get devices from a very reliable supplier that actually specs the device and follows what they say in the data sheet.
Okay, we can go to next schematic. I see on the next slide there is different schematic. What do we have here?
Yeah, this is the same analog front end, except instead of for current, now it's for our voltage channel. So the voltage, we're just measuring a differential voltage over the two terminals on the Joulescope. And you can put in any voltage you want up to plus and minus 15 volts. The way that this works is it's really an instrumentation amplifier. So an instrumentation amplifier consists kind of two stages. You have the input stage and then you have the differential stage. So the input stage is this 2197, OPA 2197 part, which is just doing a buffer. Really, it has an RC filter for EMI reasons. And then it has a filter, an analog filter in here for additional attenuation over high frequencies. And then that goes into our differential amp here, which also divides down the voltage in this case. So with the current side, we're taking 20 millivolts and multiplying that up to about some 2.25 volts. In this case, we're taking plus and minus 15 volts and dividing it down into that same range. So we're going the other way. But we also have a way that we have additional amplification here to have our 2-volt range that I didn't show on here. But the basics of this is that it really is a custom-built instrumentation amp that is designed so that it has a high voltage, relatively high voltage, 15 plus or minus 15 volts here, but then operates nicely within the rest of our instrument at the 2.5 volt range.
And from here, it goes to the ADC. Also from the first one, it goes to the ADC, correct?
Correct. Yeah, this also, because I didn't duplicate it here, it has the same second order Bessel filter that we saw in the current range. I just kept it out because I wanted to make sure it was spread out enough to fit on the slide.
Okay, then let's go to the ADC. And I think this is the Josh part, correct?
Sure, I can start
Yes,
by talking a little bit about it,
favorite
but then yeah, he's going to have a lot that he can offer because he's done a lot of work to design this part and make sure that it ends up being a great match for Joulescope, and I'm sure a lot of other test instruments out there. With the way that the Joulescope uses this part, we have this comes in right here where my mouse cursor is from either the current channel or the voltage channels. And then we just have a simple, it's a kickback filter here. So all ADCs, well, maybe not all, but almost all ADCs will have a sampling cap on the input. And that sampling cap will pull almost instantaneous current from whatever is upstream. So this filter here is helped to minimize that effect so that we get accurate measurements. And the ADC gets the right voltage, the op amp can drive it, and that goes all into here in the op amp or the ADC stage. And from the ADC stage, we now are using with this a delta sigma filter, whereas on our previous generations, we used a SAR filter. This just means for us, it's easier to drive. It doesn't have quite the same requirements for a sharp filter that we would need on the analog side. We can have it be a much more gentle filter and still get the same quality response out of that ADC.
Okay, so can we just use any ADC, or are there differences between them? Are some of them better, or some of them are...
For sure. Josh, you want to take that?
Yeah, I think I could take that. So within ADCs, you'll see multiple types of ADC architectures. So the one Matt's using here is what we call a delta sigma or sigma delta ADC. These are usually very good for great noise performance and very wide bandwidth. We also have a SAR ADC, which he's used in previous generations. Those are very good for low latency type applications. So this specific ADC that he's using here is ideal because it has a built-in wide bandwidth filter and low latency filter, as well as multiple other filtering options that help to reduce the burden on external filtering that needs to be designed. So this ADC specifically is wide bandwidth up to 24 bits. Most SAR ADCs that you'll see will only cap out at around 18 to 20 bits. The market has started to move towards full 24-bit SAR ADCs, but they're usually very expensive. So if you need a very cost optimized and good performance ADC for an application like Joulescope, a Delta Sigma is definitely the way to go.
What should be people careful about when they are selecting ADC? Is there something special?
So,
like, I don't know, reference voltage, for example, or I don't know.
Yep. So as Matt's been pushing a lot with the op amps as well, it's all about trade-offs. So with the ADC, you have to, one, be cognizant of the power consumption.
Mm-hmm.
So as the ADC starts to get higher and higher performance, it's usually going to consume more and more power. Depending on the architecture you choose, whether Delta Sigma or SAR, you have to choose between whether you want very wide bandwidth, you want very low latency, you want good noise performance, you want high speed. There are multiple different things you have to trade off between. So it's really important to identify what your specific application needs. And on TI.com, we have a lot of calculators and application notes and briefs that help explain which ADC to choose depending on whatever application you're designing for.
Mm-hmm. And can we talk a little bit about the reference?
Yep.
What are the
So
requirements?
the reference, yep. So the reference is also very important for the ADC. You usually want a very low drift reference for precision test and measurement applications because that is what the ADC base its conversion off of. So if you have a very low drift reference, you can ensure that the ADC conversion signal or the ADC code that it outputs is very precise to what the actual signal it's measuring is. So this specific reference that Matt chose is a very precise low drift reference. Usually references will drift over temperature and over time. So within TI, we try and specifically focus on creating very low drift references over temperature and over time.
So this
This
is also
enables
Texas
very
Instrument
accurate readings.
component?
Correct, yes.
I
Both the
didn't know.
ADC and the reference are both Texas Instruments.
Cool. And
Yeah,
I guess
and TI does
yeah,
TI
go
does
ahead.
make more precise references, but they also cost more. So Joulescope,
Yes.
we have some price targets too. So we can't just go out and pick always the most accurate part that's out there because there is a cost trade-off too, right? So this Ref 6225 ends up being a good performance part for the price that it's coming in at. And that's really a huge part of driving this ADC. That really is the core of converting from the analog world to the digital world, which is what we end up needing in order to see it on a screen behind me.
Yes.
I just remembered some of the op amps. Sometimes they need like not like 0 and 5 volts, but they may need like -5 and 5 or this. Can we talk a little bit about this? Because I forgot what do you use to power up your op amps?
Yeah, so this is this ends up being 2.5 volts for the analog system, actually 2.6 volts. I bumped it up just a little to get some headroom on the op amp side. But the reference is 2.5 volt reference, which is what we're actually using to go into the full scale range of the ADC. When you're designing a test instrument, you need to have overhead. That allows not only just the natural variations of the parts, but also if you say that you're going to be measuring, a 2 amp range, let's say, and you measure 1.9, people get grumpy. So you want to make sure that you have enough margin in order to measure what you're committing to, right? It's a properly designed test instrument. So yeah, the full front end is 2.6 volts plus and minus bipolar supply. One big change between the JS110 and JS220 to the JS320 is that this op amp allows us to remain on zero biased inputs. So it operates from that full scale plus and minus 2.5 volts, as you can see here, to 2.6 in, minus 2.6 in, and our
That's
signal
why
just
I
comes
was
right in.
curious how you do this. Yeah.
Yeah, we don't need to do a level shift. So one of the biggest contributors for error in the JS110 and JS220 was that level shift. So even if you buy accurate matched resistors, it's still going to be an error as you shift up because that's going to drift with temperature. With the JS320, we don't have that issue anymore by using this ADC.
Interesting. But then you need to have way actually to make this kind of voltages, correct? Minus 2.6.
Correct, and we
Another
use
Texas
other
instrument.
other TI parts. We use there's actually a trick you can do to really easily generate minus voltages using a buck converter. So we use a buck converter with an LDO to generate the plus 2.6 volts. And then we use a buck converter to generate minus 3.3 volts, and then another precision LDO on the minus rail to generate the 2.6 volts.
What about the digital interfaces on AD? Is it like important to consider which one we would like to use?
Yes. So
Yeah, it's somewhat so from a product perspective, as long as it's reasonable. I'm using an FPGA in order to communicate with this, so I don't have the constraints of a microcontroller. So if you're designing an ADC to be paired with a microcontroller, there's a lot more things you have to do in order to make sure that the software doesn't have to be crazy, the hardware can support it. But this part is kind of meant to be used with some custom logic. It can be used in other modes, but the way that I want to use it is with an FPGA. In which case, I don't really care as long as the data comes in a sensible format that doesn't add noise to the whole system. So, Josh, you had something to
Yep.
say too.
Yeah, so that's a great way of putting it, Matt. The interface really depends on the application you're using. So there's SPI, I2C, there's LVDS, there's multiple different types of interfaces. Using an FPGA is great because it allows you that customizability. But if you're using a microprocessor or a microcontroller, you usually have to be very cognizant of the interface that the ADC is using in order to be able to read out the data efficiently and not miss any bits from the ADC readout.
I'm curious because on this one I see there are GPIO2, GPIO3. So
Mhm.
is there something special inside? You need to talk to it through I2C, do some setup, or how does it work? How can you control these GPIOs? Why do we have them?
So this one specifically uses a type of SPI, parallel type interface.
Mm-hmm.
The GPIOs can be written, or you can write to the GPIOs from a microprocessor or an FPGA. In Matt's case, I don't know if you're utilizing the GPIOs in this device, but this allows you to essentially send commands from the ADC chip itself without having to directly interface with the microprocessor every single time.
Mm-hmm. And
But Matt,
how do you
and
control settings of
go ahead.
these GPIOs?
So with the way that I'm using it, and then again, this chip has different operating modes. They actually have two different interfaces essentially. There's the control interface,
Oh,
and then there's a
that's how
data
you do that.
interface.
Okay.
Yeah,
Yeah.
so at least the way that I'm using it, I have this control interface that I use to configure it, and the way that the JS320 does it is it just does this once at the very beginning. And then it's in a free run mode. It's just it's sampling and providing samples as they arrive. The FPGA is then just getting in a data stream that, in some ways, is very much like a video stream. You have an
Mm-hmm.
F-sync, a clock, so you know where your start of frame is, or you can look at this as, you know, not I2, I2S. It's the
I2S, yeah,
same,
like
similar type of
audio.
thing.
Yeah.
Simple frame, and then it just toggles as you go to the next sample, and the bits just come in the way that I've configured it in a known order. So if you're only sampling
Mhm.
from one channel, which you can do, or if the 8-channel version, they're all going to be a little bit different in how you configure that. With the way that I've selected to run this, it's only running in one mode all the time, forever. Once it gets started at the beginning of the JS320 turning on and streaming, it just keeps doing that for, until it loses power. And that samples just keep arriving. The FPGA just keeps processing them and sending them over USB. So there's very little, well, no configuration after that initial setup for the
Mm-hmm.
JS320.
Mm-hmm. Okay, so if someone would like to design this kind of precise device, what was like the hardest thing, or one of the hardest things to figure out, or maybe doing wrong, and then you finally were like, oh, now it works. Now I'm happy.
Well, there's a lot that went wrong as far as learning. Let's see, do I have that slide here? I don't. I think that's in our another one. But yeah, I did a ton of prototypes, going through trying to figure out what was the right trade-off. When I was doing the JS110, I've been an engineer for many years, so I knew a lot of approaches, but getting the right balance between what was good enough and what was possible was challenging. So you can obviously spend $10,000 and buy something that can be really good, or build something that can be really good. Figuring out how to build something that was competitively priced so that every engineer could afford definitely took a lot more of the time. So there's that balance of what works or what can work but not cost too much, I think was a huge part on the hardware side. And that's continued to evolve as parts change. You know, the JS110 to JS220 to JS320 parts that I'm using now on the JS320 weren't even available back then. So that's all been a continuous challenge. Then there's another one that is kind of outside of this, which is how do you then build this and know that it works in manufacturing? That's a whole challenge in its own right that is in a lot of ways more complicated than building the product. I've probably spent more time on the manufacturing side, you know, of how do you test, build, know that it works, as I have on actually designing the product.
We will talk about this because we are preparing another video where you will explain this. I have like two questions. Like, one, how can you, when you were designing this, how did you confirm the accuracy? And also, what kind of test you did? Like, did you do all the temperature tests to be sure like it's going to work? But you needed some kind of like more precise device than what you are designing, or?
Yeah, and as the instruments have gotten better, that's changed too. What I used to design and test the JS110 with was not accurate enough to do the JS220. What was accurate enough to do the JS220 is now not accurate enough to do the JS320. So it's not like I have one answer. It just keeps changing as things go. But you can see, you know, there's test equipment up here. So I rely on other people's test equipments. It's kind of how the test instrument, you know, test industry works. Everyone has to rely on everyone else's equipment in order to verify things. So as my needs have gotten better, I'm actually at a point now where the off-the-shelf equipment is not good enough to give a high enough test uncertainty ratio. So test uncertainty ratios with test instrument, when you measure one instrument, you typically want a test uncertainty ratio of at least 4. That means the instrument you're measuring it with is 4 times more accurate than the one you're doing. When you start talking about where Joulescopes are now with current, even the really expensive instruments are struggling to give that test uncertainty ratio over that whole range. So with the JS320, we have a different solution that we're using to make sure that it works. But yes, it's a full challenge to measure that whole current range. Measuring a much more normal current range, milliamps up to an amp, is very well known. When you start getting down to microamps and especially nanoamps, the equipment gets more and more specialized. You have picoamp meters, electrometers, but those instruments only measure a certain range. They don't measure too high, and they also don't like capacitance. So load capacitance is a huge problem with picoamp meters typically because of their architecture. So when you think about what Joulescopes are intended to measure, which are target devices that are real-world electrical products with bypass capacitors, picoamp meters don't even work, where Joulescopes do. So it's hard for us to find the right instruments to pair to
That's
measure
why I
really
asked.
what Joulescope is measuring. Yes,
So
it's
now-
a real problem.
So now people need to use Joulescope to actually reference when they are designing their own products.
For sure. Yeah. And one of the things that we do have an accredited laboratory, an ISO 1725 laboratory that tests Joulescopes. And we had to work with them to bring new equipment onto their scope in order to test Joulescopes. So yes, it's a problem.
Okay. And about the temperature range, I'm curious because you mentioned like temperature can change accuracy completely. So what kind of test do you have to do to confirm it's still measuring correctly?
Well, fortunately, we don't have to go too crazy. We're spec'd as an indoor instrument, so 10 to 40 degrees C as our operating temperature. And Joulescopes will continue to work outside of those ranges, just the specs we don't guarantee. So the 10 to 40 is relatively easy to qualify. I actually have a little mini fridge with a piezoelectric heater cooler that I control to do those temperature tests because it's a really easy range to be able to test. I don't need a huge thermal chamber in order to do that. Whereas if you're going full industrial range or extended industrial, you need a real temperature chamber.
Okay.
Yeah,
So
you
what,
need industrial oven. Yeah.
what else do you have in these slides? Because I would like to see also the demo, but I would like to see what we missed in the slides. You can start from the top. So what is?
Cool. I think you've met us now.
Oh. It's us.
But yeah, just going through, we've touched on, I think, a lot of this. We're going to see the demo here in just a moment, and I'll show this so you get it real in live view. We have, we talked about Joulescopes and people are using them. We have tons of customers all over the world that are using Joulescopes for a whole bunch of different things, but mostly for developing products with longer battery life or better energy consumption.
So it's both hardware and software engineers.
Hardware, software, we have some people using it for more on the science side as well, for some fundamental research, but mostly hardware, software, test, end-of-line manufacturing. So as you're developing battery-powered products that have a 10-year life cycle, there are new products that are coming out that have 10 or 20-year battery life, like energy meters, water meters, and they don't want to roll a truck to upgrade that. It's really important to know that when you produce one of those units, it's actually meeting your spec on the manufacturing line. So people use Joulescopes on the manufacturing line to make sure each and every one of the units coming off works.
Mm-hmm.
So we kind of skipped over the functional architecture, but now that we've talked a lot about the details, you can step back and before the demo kind of show what Joulescopes are doing.
Mm-hmm.
They're really simple. They measure voltage on one side, current on the other. As we talked about, collected through an ADC and send that back over to a host computer. And we actually have the ability to display that using our Joulescope UI, but you can also script all of this with Python, Node.js, C, however you'd like.
So usually people who are designing like test setup or something, they can use the scripts. Mm-hmm.
For sure, yeah. So initially what most engineers will do is they pull it up and just use either the multimeter view or the oscilloscope view that you see here. But then as you start developing more hardware in the loop tests, you even automating things with continuous integration, and then certainly manufacturing, you want all of those to be scripted. And we have a lot of people just using our API to do that. And that's actually gotten easier to do with AI recently. You can just tell Claude Code to take a look at the docs and give it what you want to do, what you need to do in order to exercise your equipment. And it's for a lot of things, it's pretty easy to get something up and running now.
Oh, yeah, here is the block diagram.
Mm-hmm. So we've kind of gone through this. This is where the current came in. This is the filters and op amps on the first page. This was the ADC we talked about. I've referred to the FPGA. That's this big block here. And that does a lot of the digital processing, applying calibration. So all Joulescopes are calibrated in the factory. And part of that digital processing is to apply that there. We also have downsampling on the FPGA. We compute statistics that can then be shared at a much lower data rate. People want that over the host computer.
Oh, it's isolated. I think that's what you also mentioned when we had our previous call.
Yeah, so it's electrically isolated, which is really important when you start talking about nanoamps. So when your device is hooked up to anything else, so let's say you have a target device, you hook it up to a JTAG or SWD probe, you hook it up to a UART, you hook it up to Joulescope. Each of those things is a potential different current path for the current to essentially escape from your device or can be consumed out those ports. A lot of times you don't have to worry about this. It's milliamps. But when you start talking about, measuring precision and measuring battery lives that go down to sleep currents of microamps, each little device that you attach up has the potential to totally blow your entire measurement or power budget. So Joulescopes being electrically isolated means that no current flows from the sensor side here to the USB side, which means that the current that flows in is the same as the current goes out. So when you measure a nanoamp with Joulescope, you can trust that. Whereas if it's not electrically isolated, there's ways of being clever and trying to do that same type of isolation, but it gets much harder to get that nanoamp level.
Mm-hmm. Okay, this was important to mention. Next are the three versions.
Mm-hmm.
Okay.
We took a look at. We took a look at the ADC page.
Mm-hmm.
Here we have this is a little bit more detail on that second order Bessel filter. It's just showing the frequency response and the time domain response. So all analog filters you can view either from frequency domain or analog domain or time domain. And when you look at them for different reasons, it's important to look at different domains. So on the frequency side, this is what's giving us our frequency response for the whole system. It's limited a little bit by some of the RC filters that we have out front. It's limited by the Sync 4 filter inside the ADC, intentionally so. And this gives us our designed response. The other thing that's really important for Joulescopes is they have to respond quickly. So we talked about the difference between SAR and Delta Sigma. The Delta Sigma is a little slower in the time response, but we figured out ways to manage that with the JS320, whereas the SAR was more responsive over time. The system, as we designed it with the JS320, is actually more accurate despite that extra latency. So again, more trade-offs.
So this is, for example, important when we are trying to measure on like microcontroller instruction level, for example, when something is changing very quickly. Yeah.
Correct. Yeah. So the latency doesn't matter as much when we stay within a single current range. We can compensate for that, relative to everything else. We know what that delay is. So it doesn't really matter what it is. The delay going over USB is way, way longer than any of this, right? So there's no real world response that we have to have with JS320 or any Joulescope, as long as we know what that alignment is. The biggest challenge that we have with delays is switching current ranges. So we want to switch current ranges super fast and then get onto that new current range. And with the JS320, we now have longer latency there, which means we can't switch quite as quickly as we could before, but that's actually not important because we are doing something that we introduced in the JS220, which is measuring higher current ranges as we're upranging. So we can actually measure through those current range changes. So it's a way of cheating, if you will, from an engineering perspective. It's a way of actually measuring what we care about, even though we're in the middle of switching how we're measuring that. So Joulescopes are able to measure through current range changes very cleverly, and that's one of the things that really make Joulescopes Joulescopes.
I just realized you mentioned it is up to 10 amps. That's a lot, actually.
It is, yeah, and we're not sustained 10 amps. We're sustained 3 amps. 10 amps is a lot to sustain, especially when you start talking about, well, our burden voltage is 20 millivolts up to 2 amps. So that burden voltage increases up to 10 amps. So that ends up being a fair amount of power that you're dissipating through a little teeny shunt resistor. It's not a big, beefy shunt resistor. So we're limited to about 50 milliseconds going at 10 amps. And we have a soft fuse that helps prevent if someone is going to be putting in 20 amps or something for a second, it'll shut that off. But what this allows you to do is measure inrush currents.
Yes.
So what happens a lot, and will be in the demo here, is when we have a product that you connect up, it'll have capacitance that it almost instantly presents, and that capacitance has to charge up. If you don't have the ability to measure up to 10 amps or somewhere in that range, you actually chop off that inrush current. One thing that we don't really advertise as much, but Joulescopes are pretty much the best pre-compliance USB inrush tester that's out there on the market. Just because we integrate with the USB BET test, so you can just plug it in, it just works, and you have an instantaneous test report saying that you passed, or you're presenting 20 microfarads to the USB port, and the USB forum says that's bad. Joulescopes are able to measure that inrush really easily.
You know why I ask about this? Because I know many people, they may have problems, for example, with GSM modems, because they can drive very high peaks, and then suddenly their boards will reset, or they will lose signal or disconnect, and they can't figure out why. So I think this is exactly why maybe they should use this kind of device.
For sure, yeah. And the thing with a lot of those products is that people tend not to think about your overall burden resistance. So your battery has an internal resistance. Your little teeny 28 gauge cables that you decide to choose rather than something a little more beefy have resistance. So when you're designing a product that has those huge spikes, like cell modems, satellite, LoRaWAN even, they can consume a fair amount of current, especially when those radios are turning on. You have to size everything appropriately so that that voltage drop is small. Joulescopes are designed to make sure that they don't contribute to that problem, but it doesn't help you without doing more measurements for solving that problem if you already have introduced it to a product.
Yeah, but it's good to see that, there are I designed for 1 amp, but actually there are peaks 10 amps. Then maybe I should add more capacitors.
Yeah, I mean, a big part of engineering, especially of electrical engineering, is making the invisible visible. I can't see electrons. I don't think, as far as I know, no one else can see electrons. Um, so we have to rely on test instruments to do it. And if you don't have the right test instruments, you're just guessing. And that just consumes time, consumes effort. Whereas if you can just get the right test equipment affordably enough, it makes things so much easier.
Okay, next. What do we have next?
So we talked about the different types of op amps that we have here in order to achieve, the huge range that Joulescopes are able to do, and just choosing the right products for the right part of that signal chain. And that dove right into the signal chain. One thing we didn't talk about too much, I just skipped over the voltage here, is the zero drift op amps, also called chopper op amps. They are pretty unique and interesting in that they are designed so that they switch their polarity at a frequency so that they can cancel out any offset error that they have, because there's no way to design perfect silicon that has no temperature correlation at all. If someone develops that'd be really
We've
cool.
tried, but yeah.
I'll be looking out for that. But one thing about, it's a joke. Everything measures temperature. Some sensors measure other things. So getting rid of that temperature effect and aging effect, which is also related in a way, is very challenging. And chopper op amps, if I go to the next slide here, they do this switching and then essentially decide, if you will, they integrate to figure out what that difference is and maintain that so that they self-cancel out the offset error that you would normally see accumulated in other op amps.
I think Josh is exactly, he knows exactly what we are talking about.
Yes. So actually on the previous slide, you did cite that white paper there, which explains it in a lot of detail. I would definitely recommend checking that out because these chopper op amps are a great resource because it removes an error source that you would have to worry about in your error calculation. So these op amps being able to switch the polarity and remove that error over temperature, error over time, makes it it simplifies the overall error calculation and makes the overall signal chain easier to design.
So
this technical white paper there is a good resource to check out.
When people have to start worrying about the things like this?
So
theoretically, yeah, Matt, I was going to say theoretically, as he was saying, everything measures temperature. As electrons run through circuits, they're going to heat up. They're going to generate heat. It's going to cause some sort of drift in the measurement itself. So as soon as you plug in something, it's going to cause heat. It's going to cause some drift over temperature. If you intend for something to run for a long time, you're likely going to face drift over time as well. Because as hard as we try to design things to last forever, they're going to degrade slowly over time. So essentially, if you want something to last long, if you want something to be able to power on, you're going to have to worry about drift over temperature and time.
And for what kind of precision? Like, because maybe if someone is measuring, I don't know, 2 volts, is it still going to influence around the 2 volts or?
So at a very high level, like 2 volts, you probably won't see too much. Of course, you may want to account for some sort of offset, but it won't affect the measurement too much. But when you start getting down to the nanoamps, as Matt was saying with Joulescopes, that's when it really starts to affect it.
It's also with a lot of things like op amps and ADCs, it's percentage of your full scale. So, and all the TI parts have great specs on this. So if you're measuring 2 volts, or 2.5 volts like reference, and you want to measure a signal that's at 1 volt, it's going to be pretty accurate. And pretty accurate is left as an exercise to the reader. Now, if you try to measure something that is, 0.0001 volts, and your full scale range is 2.5 volts, now you have a dynamic range problem. And that's just fundamental of engineering in any discipline almost. But when you start talking about percentage of what you are measuring as full scale, things get harder. So if you're measuring 1 in 10, human eyeball, we can do that. 1 in 100, almost, we're getting there, but now you're talking about moderate engineering. 1 in 1,000, you're now talking engineering. It's not something that just happens. That's a 10-bit ADC, 10-bit precision of actual effective number of bits. When you talk 1 in 10,000, you're now at that 16-bit ADC. This is, precision engineering. And with Joulescopes, we're going to be pushing, well, over the full range, we're effectively 36 bits, but we cheat in a way by switching shunt resistors. The actual range is about 16-bit, and that ends up being pretty serious engineering.
And that is a good point you brought up, Matt, is you brought up the effective number of bits. So a lot of ADCs will list the total resolution that they can measure, but due to error sources, you'll actually get less resolution output from the ADC itself. Because when you start to get in, factor in the gain offset, the temperature offset, the reference drift, sometimes ADCs have references inside of them, the actual effective number of bits you'll get will be lower than what the ADC itself claims it can output. So that's another thing to be cognizant of when you're reading the ADC datasheet and choosing an ADC.
And sometimes by a lot. So it's some of the competitors out there in the microcontroller space, they'll say they have 16-bit ADCs, but you only get 9 effective bits. That's kind of common for a lot of microcontrollers that are out there
I
on the
never
market.
really noticed this. Very important.
Yes, so it'll still output 16 bits of data, but a lot of it will just be
most
noise,
of them are rubbish.
and then you'll get actual 9 bits. Sometimes, yes.
I didn't know. Okay, we can go to the next
everyone
one.
says 16 bits. We're good.
Yes,
But no,
that's
that
exactly
doesn't mean
what I see in datasheet. Yes.
Yeah, the devil's in the details, right? So isolation, we talked a little about isolation and how that makes great measurements for Joulescopes and keeps things from finding other paths. And some other points that we kind of brought up here is how do we end up designing a full product that actually works well, figuring out how to manage and maintain noise throughout the circuit. So a lot of people will just throw down ferrite beads in analog designs. Ferrite beads are resistors and inductors. And the problem is that inductors, when you have a capacitance out there, which is your bypass capacitance, form resonant circuits. So in a lot of ways, you can make things a lot worse by adding in ferrites. Unless you know a lot about your signal characteristics and where your peaks are and where your noise is and the full power supply rejection of your every component in your design. So a lot of times, if you can manage the energy consumption, so reduce currents and choose lower current parts, then you can actually just put in like small value resistors. Like in the case of one place with the Joulescope before the LDO, we put in a 1 ohm resistor, and that's it. That energy is going to be dropped in the LDO anyways, but by putting in a 1 ohm resistor, that forms an RC filter that ends up attenuating with a breakpoint of 16 kilohertz. So when we're talking about looking at our frequency of interest, for some other things that go on in the system at 500 kilohertz, 1 megahertz, that ends up dropping at least 20 dB with just a simple RC filter with no possibility of resonance. So there are a lot of circuits that I've seen over my days that I've recommended that you very carefully consider or remove your ferrite beads.
Actually, this is something what when I was designing boards like maybe 15 years ago or something like this, then there were many recommendations to place ferrite beads into power rails and this kind of stuff. And some time ago, I've done a video. If I find it, I will post it somewhere here. And it was very interesting because I did these simulations, and exactly between the ferrite bead and where the capacitor is and where the power pin is, it created a kind of resonance circuit. And for some frequencies, it actually did power actually was not delivered to the pin for some frequencies because of the resonance. So I think many people, they don't realize this, or they may think like it just goes through. Yeah, it goes through for some frequencies, but for some frequencies, it may not go through completely.
Yeah, for some designs, people just think they're magic. You sprinkle them down and they get rid of noise. And they are, if you compute everything.
You sprinkle correctly. Okay, when we started about this, we still have a couple of minutes, so I would like to talk a little bit about maybe layout challenges and placement challenges, because many people they ask about, I have this digital circuit on my PCB, I have this analog circuit on my PCB, do I have to split grounds? Or what is your opinion on this when you were designing this kind of product, the layout and component placement?
So splitting grounds it just causes problems unless you know how to manage it. There's two things that happen. One, return currents have to go somewhere. So if you have to cross a signal over that split ground part, that's really bad. You're going to just create an antenna and slot antenna that's going to radiate. And in addition, the return currents are going to go somewhere else and mess up your signal. With the JS220, I actually did have a slot for managing I had some really noisy digital things on one side, and I did put a slot. Everything went around that slot, so there's nothing there. And that was good for the JS220 because of how some of the layout things had to happen on that design. With the JS320, it is a solid ground plane on the sensor side, solid ground plane on the host side. There's, because it's isolated, there is a split there, and there's always been. But there's no split on the ground plane. I've managed with the JS320 to keep the sensitive analog stuff way away from all the noisier digital stuff. And that seems to be doing well at managing that noise level.
So the placement of the analog and digital components, that's what is really important. Keep the solid ground plane, and people don't have to worry that somehow some currents from the digital part will go to the analog part.
Yeah, and it's really placement is part of it. I mean, if you can place things far apart, that makes everything easier. But it's really, where do the currents go? So if you have a digital signal, even though the part's way over here, if there's a digital signal that goes right through your analog stuff, then you're introducing those digital edge rates into your analog. And it's really edge rates that matter more than anything for noise pickup. So if you have super slow edges, it doesn't really matter what's going there, that the DVDT coupling doesn't happen as much. Whereas if you have super fast edge rates that you're not controlling, so you didn't put any series term resistors or whatever on your digital, then you'll end up radiating more noise between your sensitive, or to your sensitive analog from your digital. One thing that was on here, these little resistors, these are on the ADC. You don't really need them. But if you don't put them, then your edge rates are going to be a little bit higher. Now, this part does, I think, pretty well, but I'm just abundantly cautious, and they only cost, a fraction of a penny. So why not? I don't want to take my risk right where my analog circuitry is at having fast, untamed fast digital. So by thinking about edge rates and how do you manage that, terminations, because anything that rings and reflects back and forth just creates even more edges that end up radiating into your sensitive analog, and also they can help you or hurt failing compliance testing, so for radiated emissions.
Josh, does Texas Instrument have some good documents about this? Because you always point out to some documents. So.
Yes, we do have some good documents on our website. Another thing I do want to bring up is the clocking signal. So when you write the trace for the clocking signal going into the ADCs or any other analog component, it's very important that you make sure that the clocking signal itself reaches the components at around the same time, especially if you're trying to synchronize multiple of the components together so that the rising clock edge occurs at the same time. Now, some of our ADCs do have internal features that can allow them to synchronize the clock edges, but with the clocking signal itself, if you can try and make the trace lengths about the same, or if the parts are far apart on the board, make sure that the clocking signal itself reaches the part at the same time. This allows to save a lot of burden down the line, where if you need to synchronize multiple components together, or you want to try and read out all the data from different parts of the board at the same time, we have a lot of collateral covering that as well on ti.com.
Okay. What about the op amps? Do you have some? I'm thinking. Oh, I've done one video with Arthur, I think, or maybe even two videos, which are really good about op amps. Okay, I will put them somewhere here.
So that white paper, I think, was actually written by Art K.
Okay.
Yes, he's our op amp guy. He's very great.
So if someone would like to learn a little bit more about op amps, then watch these videos. They were super useful. Okay, I think this was the last slide. Then there was the demo.
Yep.
Okay.
So we can switch over. I can switch the screen so we can see the demo a little bit more closely.
Okay.
So let's do share to this one. Share. Okay. Can you now see?
Yes.
Oh,
yes.
You do see that one? Okay.
Mm-hmm.
And we also have a down camera, so the top-down view here of the setup. So let's see here. Let me get my mouse so I can drive it. And on the right screen.
You can explain what do you have on table first.
For sure. Okay, so what we have here is we have two different demos. We have a demo with the TI Bluetooth chip, and we have a demo with a bunch of other things here. We'll start with the one on the left. We have a Joulescope that is getting power over a USB-C connector here. And then that goes into this little switch box where we have a number of switches that we can press. But it also has one that's going out that's always driven, and I'm touching this, so I'm causing piezoelectric effect. But once we have this going, we have a little teeny Raspberry Pi Pico that is just driving a bunch of signals here so that we can see something at the super low end of the response. So this is looking at something that's peaking at about 6 microamps. So it shows that Joulescope can do really well at the low end. The first thing we have that we can press a switch for is this LED. When I press that LED switch, we instantly jump from these microamp ranges all the way up to here about 13 milliamps.
So we are measuring, I'm sorry for interrupting, we are measuring the current of the Raspberry Pi, correct?
Well, we were measuring, actually, there are a bunch of resistors here that it's twiddling. So the Raspberry Pi I have powered over USB, but it's using MOSFETs here to control a bunch of different shunt resistors. Yeah, so that's how we're able to get that super low current. Yeah, and on the display here, we're seeing current, I didn't explain this well, voltage, and power. So the three curves that you typically care about, the integral of that, of charge, or current is charge, the integral of power is energy. And we can use Joulescopes to measure that. So we can take a look here, add dual markers in, and we'll take this a little better look at this in just a moment. But you can look at the average current, the integrated current, which is charge, the average power, and the integrated power, which is energy, just by using dual markers. And that's how you can make super easy measurements on products that you're building or any target device that you have. And
I think you can use these values to basically calculate, for example, how long your battery will last, correct?
Exactly, yeah. So we have some requests to make that even easier for people. The problem is that everyone has a different opinion about how that needs to be done. So we have not tackled that as directly as the industry would like, and that's an outstanding problem that we hope to solve in the not too distant future. But right now, just by knowing that energy per event, you can then add up your events per time and then estimate the total amount of energy in your battery. The thing about batteries and powering your devices, it really depends upon how you're powering it. If you go battery direct or battery through an LDO, you care about current because the current is maintained across that. Whereas if you use a DC to DC converter, you care about energy or power because that's maintained across the DC to DC converter with some loss. So depending upon even how you have your target device set up, you care about different things. So going back over here, we took a look at the LED here.
So every button is doing something different. Yeah, one button is switching the LED, other button is doing something.
Correct.
Okay.
So this one is a little fan, which you can't feel. I can feel here, but it's a nice motor. So motors produce really interesting waveforms. A lot of people think, oh, I have a DC motor. It's just a constant current thing. That's all it is. Well, it actually is this inductive load curve as the motor coils switch and as the motor rotates. And you actually can see here how many times a second that this is alternating and see a nice little curve waveform on that current.
So you can calculate the speed of the motor.
You can. So if you know enough about the motor, I just bought this one, so I have no idea. I could probably figure out, how many times that it has to switch per revolution. But once you know that, and if you're building something based on a stepper motor, you definitely know that. You can estimate the speed just by using joule scopes. Yeah.
Okay.
It's kind of cool. So people are using these like for robotics type applications where this is now super important for all the new AI robotic stuff. And Joule scopes for not the main drive motors, but for all the more sensitive motors all work really well. Then the last
200
one here.
milliamps. Yeah.
Oh,
No,
what?
I was just checking like 200 milliamps for the motor average.
Oh yeah, yeah. Well, this one we're going to see the inrush current from Happy Dancing Cactus over here. Good afternoon, Cactus. Oh, he shorted out. Okay. Good afternoon, Cactus. There he goes. Okay. So with the Cactus here, when I press the button, remember where I was talking about inrush currents? So this spiked at about 3.5 amps right here.
Wow.
So we were able to measure that inrush current. So we went from nanoamps over here all the way up to 3.5 amps. So just showing how Joule scopes can seamlessly switch. We're now looking at these dots are samples. Joule scopes sample at 1 megasample per second. So we're looking at 1 microsecond intervals. So we went from almost nothing right over here, 100 nanoamps, all the way up to 3.5 amps in microseconds.
5 microseconds.
But then we get, yeah, it's super fast. And then we get to see the dancing cactus, which you notice there's a little of that waveform like you saw from the motor before for the fan, coupled with some other things in here. He's doing the song and dance and lighting up. So you see the whole waveform. So let's switch over now to the other demo that we have, which is much more of a real product, right? So if you're a firmware engineer or a hardware engineer working on like a BLE device, this is much more what you're thinking about. So let me switch to the other Joule scope. So we have both Joule scopes here. I'm going to switch over to the other one. We can have multiple simultaneous Joule scopes with the UI, and they can work together. But what we're seeing here is the device turning on periodically. I have this beaconing at one beaconing cycles per second, essentially. So and you can configure this part to do whatever you want. I just did this for a demo so that it's happening often enough for us to take a look at it. So what I can do here is zoom in on one of these beaconing events. This is what happens when this product turns on. And this is, let's see the part number here. This is, I don't know if can you see that in the down cam?
I can see the board, but not the
CC2340 R53 development kit. And I'm just powering it here from this little teeny desktop supply. It's a really cute miniware supply that comes in from USB-C, and it's just generating 3.3 volts that ends up powering the board. And then we're just using Joulescope to measure that. So in this place here, this is one of the beaconing events for the TI BLE chip, and it's consuming about 12 microcoulombs of charge or 39.8 microjoules of energy. So let's say you had a battery target where you wanted to last for a year on this. This would allow you then to say, I can afford this many events per day of this. Likewise, we can move this over to the sleep current here. Let's go over here and make it a little bit bigger since there's some variation. But it's consuming about 150 nanoamps of sleep current, which is very impressive. BLE devices, continue to get lower and lower power. This is one that's really showcasing how low that sleep current can get. And then what we can do is we can, oops, let me go over here. Oh, I have to click on it. And let's, I have a keyboard here. Let's go. Hard to look both ways. Let's do it for 1 second here. Exactly. Oh, there we go. So I'm just going to spread this over. Because we know we're beaconing once per second, we can then look at this total thing. The beaconing plus all the sleep current ends up being 42 microjoules. And I think I said, 39 just a moment ago? So most of the energy right now is being consumed in that beaconing mode. So the trade-off, the sleep is so good compared to that beaconing energy that at once per second, most of that energy goes to the beaconing. So if you reduce that, then your sleep current becomes more important. So let's say we switch to beaconing once per minute. now your sleep current and your beaconing current may get closer. At some point, they'll end up being the same. And when people are designing products, designing both for active mode and sleep mode ends up being more and more important as they're trying to get longer and longer battery lives.
And I would like to point out, can you zoom in again on this beaconing sequence?
Sure.
Like,
Let me just
that's what I mean when I always mention like on instruction level. So basically, we are almost see instructions how they are executing and what part they are switching on and off, and correct?
Yep. Yeah, so I don't know exactly what this chip is doing. I'm not familiar with a lot of the details, but you can see here there's an initial, this looks like an RC decay, so it's turning on something internal to the chip. And then it's going and doing a bunch of different actions. So some of these are going to be BLE transmits, when it's pushing out some information over the radio. Some of it, this flat part and this flat part are probably more on the software side, I guess, of it just managing and setting up for the next interval. So this is using FreeRTOS internally. So it's doing everything that you need to do in order to have a microcontroller go to sleep, wake up, and be low power. So there's a bunch of register transactions that are happening probably both here and here. But again, I'm just hypothesizing.
Yeah, but without this kind of measurement, I think it would be super hard for software engineer trying to optimize battery life.
Oh, for sure. And you don't necessarily need to know everything that's happening here, because if you think you are doing something in a range, so you can toggle the GPIO. For example, if I was developing this and I cared about the initialization and finalization time, I could easily toggle a GPIO here, which you can add to Joulescope. So Joulescope has GPI inputs, and then you can see exactly when you start to enter that region and when you exit that region. And as you optimize, you can then instantly see the changes that you've made, so whether they've been effective or not.
So basically, you can toggle GPIO around the instruction which is interesting for you because you are doing something special and you would like to know current consumption exactly when this instruction is executed. Then you tie it up to GPIO, and basically this is used like some kind of flag or interrupt. Yeah, you can see it then.
Yeah, you can use the GPIOs however you want. So we have four inputs, six total, that you can connect up to your target device. And that's usually enough. By the time you get more than that, you're working on something else entirely. So having one or two GPIOs is usually enough for most applications like this, unless you want to go more of power profiling the exact firmware code. There are some tools out there that try to do that. Joulescopes with some help do that, but not on their own.
So, and then basically you just add this GPIO into this graph and you will see, okay.
Yeah. So I don't have the GPIO connected up, but with the Joulescope, you just say, I'm on this one right now, 0, and then add in 0 down here and go. It's a really boring thing because there's nothing connected to the GPIO port right here, but we provide a cable to make it really easy. And those GPIs are designed to be low current. They are not isolated, so if you want to keep the isolation and have your good sleep current, sometimes it will work if you don't connect anything else to your target device. But we do recommend some isolators that you can buy and design in. And now, TI, we use the ISO 7762 inside the Joulescope. You can use that part or any of the other ones from their portfolio that are really, really accurate. And they have a new part that is isolated DC to DC converter as well. So if you start thinking about designing your own test instruments to connect up, which people do when they are developing products that are super low power and where energy really matters, you can actually use those parts off the shelf now with almost no effort. They are, it's a lot easier than it was when I was designing the JS110, 9 years ago.
Okay, now I have a question. I think some time ago I made a video where this guy, he mentioned you can change the panels to make some measurements easier, correct?
Right.
I would like to highlight this because we didn't really talk about how exactly it is connected, but I think you can have also like USB panel or...
Yeah, and I don't have one within arm's reach right now, but this front panel here is actually a circuit board, and it just connects in. I have a better example just sitting right here. So you have, the lighting is not set for there, but you can just disconnect this and you can, there's just two screws to take apart the Joulescope. There's a YouTube video if you want to link to it of how you do this, because I think it was the JS110, but it hasn't changed very much. We actually have two screws rather than four, which the JS110 had, so it's even easier. But we sell a number of these different front panels. We also have drawings and KiCad base design so that you can easily customize it. We've had people contribute. There's one that is the USB all the things one. It has every single USB connector plus terminal blocks that a customer designed, and it sells on Tindy. We have a few other ones as well that the customers have contributed. The bigger case that we've seen people do is actually just take out the circuit board and use this directly for factory automation. And just that's your terminal, your connection to your device under test, and you just design this into your fixture.
Is there anything else what we would like to mention in this video?
Yeah, we have a few new things to mention before we wrap up. One thing that I created was, we talked about a lot of the parts that were on the Joulescope, the JS320, but it's really kind of cool to see them all. So where they are, so we have the connector that we were just talking about, which is where the sensor goes. And then we have our first stage op amps that we saw in the schematic for the OPA 387, the OPA 388s, the Bessel filters plus an extra one for regulating the GPIO voltage, the front end OPA 2197 for doing the voltage. We have some comparators as well. We didn't talk as much about the analog switches, but the TMUX 1108 helps make Joulescope switch between the current ranges. Another one that we use for the GPIO reference voltage, the reference we talked about, the ADC, and then a bunch of power regulation parts. This whole script comes out of KiCad, and spent a little one night with Claude trying to figure out how to make a nice little animation here that looked visually appealing and cool. So you'll be seeing this hopefully on media as well.
So all the black chips are Texas Instrument chips?
Yep.
There are many.
Yes.
They make good chips that make Joulescopes work well.
Okay, I would like to add. Very often when I'm designing boards, actually, I select Texas Instrument as the manufacturer of the chip. This is not paid advertisement or anything. I just do it because, from my experience, it's one of the most reliable selections. So I know when I select the chip from Texas Instrument now, I will be able to buy it. In past, it has happened to me many, many times. If I use different kind of manufacturers or random chip manufacturers, what may happen one day you can buy it, other day you may not buy it, and then after 1 year the company may disappear completely. So that's why I really like to buy components from good chip manufacturers.
Yep, and the Joulescope products, yeah. I mean, I have the ability to select from any vendor that I want, and you can see what I selected.
But I understand this because then once you are designing this kind of product and you use many components from same company, it's also maybe good for the company to make collaboration with you, exactly what you are doing right now, because they know your product can be used for good promotion of the chips. And I think sometimes this doesn't happen.
We especially admired.
Yeah, some companies, they don't do this.
Sorry, go ahead, Robert.
Yeah, some companies, they don't do this. I've done some designs with some chips, and I made them open source, and I made them quite complicated, and these chip companies, they never recognize me. So I'm very happy Texas Instruments is actually doing this, recognizing people who are using their chips, and also making taking special care of these design engineers. So thank you for this.
Yep, and we especially admired how Matt was able to build his entire board without too much help from the Texas Instruments side. We learned about the Joulescope board that he was building after we started engaging with him once he was most of the way completed. And that was a great thing on our side because we were able to realize that we had the collateral on TI.com to help enable engineers to design their signal chains. And it was good to see Matt, the passion he showed for Joulescope, as well as using the TI parts to help enable his solution.
This is also good to mention. So you didn't like sponsor, made, or push him use Texas Instruments, no.
No, I mean I've been hoping that TI would notice for a little while, but they finally did. One of the big changes, and we can talk about this another time. On the business side, they've helped to support us now with a backlog account, which just makes a lot of our ordering get a lot easier. So TI, has been a great partner. Now that we have a little bit more closer relationship than we've had in the past until, back in, November, December, I didn't have an inside salesperson at TI really doing anything. I just order on the TI web store or Mouse or DigiKey and just do my thing. Now with the JS320 launch, we're a little bit more closer on the collaboration side. And they're helping to support me so I can be successful as a business with that backlog account, so I can actually forecast parts and ordering over time, which, when you start getting to a certain size, is super important.
Mm-hmm. So your latest Joulescope has not been released yet, correct?
It is coming out very soon. So the end of June, we are launching it. You can check in on the Joulescope website for more details as we get a little closer. I think by the time most people see this, we'll hopefully have a little bit of information out there. But it is coming pretty soon. We've passed compliance testing, and which is like for every engineer the last big hurdle of stress. That was just last week, and we're moving towards ramping up the production and launch.
Okay, so I think when the video will go out, then it will be very close to the launch, so people should be able to buy it very soon. Yeah. Okay. What else? There is this. This is the last page, correct?
Yep,
Yes,
that was
I
the
do
last one that we
briefly-
just skipped over.
Okay.
Yep, and I do just want to touch on, we discussed a lot of TI parts that Matt has using in his Joulescope, but beyond even that, we have a very broad portfolio that's targeted towards precision test measurement applications. So even if the part wasn't mentioned today, we likely have something that can fit for the power side, the analog signal chain, or even on the embedded processing side that can be used and to enable a wide variety of test and measurement applications.
Okay. So here is the list.
Yep.
Okay.
These
I
are all
think
the
this
things
is
we
the
didn't
list
talk
of just
about.
what Matt's using. Yes, but we didn't talk about today. Yes.
So yeah, we could talk about each of these parts, but they end up, a lot of them are much more common parts, except for the precision analog supplies. But again, they make great parts across the lineup. And I selected these not just because they were TI, but also they're the ones that were cost effective and got the job done. So they're good parts.
Okay, perfect. So I would like to remind everyone, we will be doing another video with Matt and talking about designing process, manufacturing, even like marketing. Am I correct? And so watch out, there will be another video coming soon, or maybe it's already there, just people can watch it. And if there are any questions about Joulescopes, then leave them in the comments. And there is one more thing. If they would like to contact you, here is the contact, matt@joulescope.com.
Yep.
Or,
and I'm also Matt Liberty on LinkedIn, if you'd rather use LinkedIn. And the website, we also have a forum. So if you have any technical or detailed questions that you want to share publicly, forum.joulescope.com.
or you can show your company website so everyone knows, where to buy it. How much does it cost? That's the question.
Yes, so let's pull that up here and type in, went above, joulescope.com. There we go. So this is before the JS320 launch. This is still the JS220. So we'll be updating this website. So by the time you visit, hopefully it'll be showing the JS320.
And there is, I see, shopping cart, correct?
Yeah, so you can go to the JS220 here, decide if you want the factory one or the NIST traceable. If you don't know what you want the factory one. This is for people doing more medical, industrial that require that. add it to your cart, and it's as simple as that. This is a Shopify web store, so you've seen probably a bunch of them that you've ordered from.
Now, before we completely finish, because I think everyone see this and they will be like, it's $1,000, it's $1,000. So can you tell them a little bit more why it's worth $1,000?
Sure. So Joulescopes are trying to hit a sweet spot of price. There are things out there that the semiconductor manufacturers supply that are more affordable. They're meant to just give you a sense of where things are, whereas Joulescope is a test instrument. It is meant to be accurate, calibrated. We are able to get ISO 1725 calibration from an accredited partner. So even if you don't get that, what it means is that someone other than us can say that Joulescopes do what they say they do, which is important. So you can trust it as an instrument, not just as it's somewhat close. Joulescopes are accurate, right? So it's the product that when you go to doing engineering, it gives you that level of engineering confidence without breaking the bank. The next step up from this is over a price order of 10. So Joulescopes are aimed to be affordable enough for any engineer that is doing work on these type of products. And if you're launching a product, your company is spending way, way, way more than this in order to develop that product. This is what allows you to design a product with long battery life, excellent energy consumption performance, without having uncertainty. It removes the uncertainty of product development, so you don't get surprised when you go to the final integration test and your battery dies in 3 days. You can know with Joulescopes up front that your product works all the way from like day one through the end, through continuous integration, through factory test, and it's priced in a way that every engineer that is working on this in a team can actually have a Joulescope at their desk and be responsible.
Okay, thank you so much, mate. Thank you so much, Josh, for helping me with this video.
Thank you.
That's all for this video. I hope it was helpful. If you would like to learn more about electronics and board design, check out our online courses. You will find everything important there, from basic board design up to advanced board design and high-speed PCB layout. We have courses in Altium, Cadence, KiCad, and also courses covering many different topics, for example, FPGA, EMC measurements, and so on. Visit our website at fedevel.com. That's all for this video. Thank you very much for watching, and don't forget to leave your comments. See you in the next video. Bye.